Hello and welcome to the recording of lab4's source files. I'm going to be going through the basic files of dual port memory, drop FIFO, detect 7 bytes, register for 9 bytes, word match, comparator, and compare 8. I'm starting today with the dual port memory IP core um, generated component. A lot of these are project options followed by parameters. Um, it has things like write depth and different enables and generally tells the ISE what it can do and what it cannot do, this component. I'm then moving on to the drop FIFO for a uh, top to bottom view of this of the pattern matches functionality. Here I have the basic module for the 8-bit register, followed by the 8-bit clock enable and loadable counter, the 8-bit counter without a load, the compare 8, the drop FIFO itself finally. So this has a number of different components. A lot of them are just registers, either for 1 bit of data or a byte. As you can see, this one is for the loadable counter. It takes in the loadable counter's output and hold it for 1 clock cycle so it can be compared with the non-loadable counter. As you can see here, we have the comparator for this old loadable counter value, so the counter value of 2 clocks before this compare 8 is used, as well as the uh, non-loadable clock, or what I call the basic clock, or counter, pardon, loading with the uh, loadable counter value 1 clock before this compare 8 is executed. We have the loadable clock right here. So it lets you load this D input if XL-XN36 is high, and outputs that for Q. If not, um, it is a basic counter synced with the clock with an overflow and a clear and a clock enable. This is the basic clock. It just has a clock enable, a clear, and an output that goes from 0 to 8 or 0 to 7. This is our 9-byte register, pardon me, that holds the input data for 1 clock cycle before going to our dual port memory here in order to be output um, with the uh, output for our non-loadable counter and the output for our loadable counter. Moving on to detect 7 bytes. This is a very simple module. Or no, this is one of our more complicated top-level modules. It has a word match, a basic uh, register, register with our clock enable, and our bus merge component, which you'll see later, and our 9-byte register. What this does is it takes 2 inputs, merges them with our bus merge component, and runs part of that through the uh, word match module. It runs part of it through our, or it pardon, um, and also takes in our hardware register A, and it does the same for our wildcard, which is our mask. So we can see the inputs themselves are pipe 1, which is a 9-byte register. It takes the last 8 bytes, merges them with pipe 0, which is actually just pipe 1 but held for 1 clock, and inputs this into our word match system. If the words match and we have a match enable, we also have uh, a signal here to make sure that we are able to write to this output. It outputs that signal. It propagates the fact that we have a match and puts it in the register for one cycle, and then outputs that as a matched byte. This is our 9-byte register. It's very, very simple. All it does is take uh, 4 modules, 5 modules, sorry, um, 4 2-byte modules, so 16 bits. That's 2, 4, 6, 8 bytes, and one 8-bit or 1-byte register, and concatenates them together. So it acts as a register for 9 bytes. Here we have our word match module, also fairly simple. It compares 8 words. Um, it compares them with our data in going 1 byte at a time through uh, each, or it goes 1 byte at a time through our data in, scanning every word length, comparing it to our data comparison and our wildcard uh, comparison mask. It does this 9 times, I believe. No, 8 times, pardon. And if any of the word length strings match the pattern we're given or is passed through by the mask, we output a match signal. Here we have our comparator stated 8 times within our word match, and uh, it's also a very basic component. We have 8 compare 8 or 1-byte modules. It scans all of these and sees either if there is a match or if the mask is enabled for that byte. And if either we have a match or the mask is enabled, for every compare 8 module, we output a 1 on our match signal. Compare 8 is the simplest of all of our designs. All it does is take in 8 bytes of data from an input and an output, and uses an XOR gate on each of them to see if B7, A7, B6, A6, etc., all the way to 0 match. And if the top half matches, it outputs a 1 on this and 4. If the bottom half matches, it outputs a 1 on this and 4. And if both and 4s output a 1, we output our equivalent signal. Thank you very much. We're now going to move on to part 2. Thank you.
So in order to easily communicate with the FPGA board and update our files, we put this config file in our .ssh so that we could access the machine. As you can see, I'm SSHing into the host FPGA that and put our password. We can see our IPs. So before we uploaded our custom bit files to the FPGA, we programmed it with a reference NIC design. And in this configuration, all the packet forwarding is handled by the Linux kernel. You can see our performance. The performance from between the FPGA and the nodes was about 135 to 145 megabits per second. Then we tried it with the reference router. And the reference router basically just makes it operate as a router, and it's already a design that we know works. So using these was partially also to make sure that our whole hardware was working properly. And we can see the router performance, it almost doubled to almost 250 megabits per second per node. We also use RKD, which is a routing kernel daemon, which reads the routing table from the Linux kernels and programs that was used over here into the NetFPGA's hardware routing table. So it allows the packets to bypass the kernel. Packets to be forwarded directly in the hardware using memory-based lookup. But you can see our performance did not really improve. So finally, we load our custom design into the flow and for the user data path to filter out bad packets before they're routed. And this is our design that Nick explained, where packets can come through and through our drop FIFO and they'll get sorted out depending on if they match and if drop FIFO is functionality is turned on. So basically, incoming packets will enter our FPGA. They'll first be set to the arbiter, which selects packets from these input ports and forwards them into the user data path, which we have set in our design as IDS, and it'll go into the IP router, which will send it out to where it needs to go. So when we upload our design IDS reg, we'll basically add the hardware right through here so that this can drop packets that are bad, aka the ones that have found our sequence within the message. So there can be bits here. The program will use a sliding window to look across. And then if it finds that sequence, then the packet will be rejected.
Hello, here's the demo for NetFPGA. So when we access to the lab4.h from our library, so we will find the address for our high pattern register and low pattern register, also like IDS command register and the matches register. So once we have the address over here, we copy it to our IDS register file. So we modify the write function and the read function on provided IDS register file so that we can run our write and read function on our NetFPGA. So let's see how it goes. So we have our two files. One is IDS register, which is SCP from our local device to our NetFPGA, and also we have the generated .bit file. So what we have to do is we have to do the nf download nf2 .bit file. Okay, once we download it, we have to do a RKD, run the RKD software, and we need to cmodify, make our IDS register to be a executable file. Okay, which is right here. So how we do is like let's check the register was inside the address. So we can see the values for match register, values for pattern high register, and the value for pattern low register, and the value for command register. Okay, here we go. Now let's do a simple test. We do write the simple 1 2 3 4 4 bytes to our register. So yes, so it says like we read the value to 200, which is our pattern high register. Okay, let's see how it goes. So we do a IDS register read. We'll read our value over here. As you can see, we can also to do all registers to read from our pattern high address. Okay, now let's move on to the part H on our lab instructions. So we need to write a byte test and then we reverse it. How we do that is we modify the direct file over here. So we put our swapped, we do shift and swap our orders. So after we save it, we need to SCP the IDS register file to our netFPGA again. So type the password, then it's transferred successfully. So what we have to do is we have to make the IDS register be executable again, and let's see how it goes. So what we have to do is we need to do the IDS register write. What we write is we write A, B, C, D, E, F. Okay, so we read A, B, C, D, E, F to the register, so we can do a simply read function. So we read a reverse version of our strings. So this is good. Okay, so let's clear our reverse function, and we do copy the file to our netFPGA again. Okay, after that we do a change to executable file. So to the next, we need to do a pattern. So what we have to do is we put the pattern ABCDEFG to our IDS register. Okay, it says we're setting the pattern to the high and pattern to the low. So what is this? It is we split the 8 bytes to 4 bytes. So 4 bytes on the high register and the 4 bytes to the low register. And we can always see in here all registers. Okay, we have high and the low, and we also see the pattern matches. So when we tap at the register matches, it will print out the matches value, which is over here. So for next, we want to run our RKD software for router. Okay, let me queue all RKDs, and we do the RKD software over here. So what we did is we set on node 0 as a server. We tried to use iperf-i options, but it turned out our iperf version is very low, so it won't possible for us to transfer the packages. So what I have to do is we use the NC, which is netcat, to the address with the port in the UDP. So when we run it, we put A, B, C, D, E, F, G patterns to our node 0. Okay, so it says nothing because it will drop the file, so it won't successfully transferred. So what we have to do is we can check our matches. It shows 1, which is correct, because we sent 1 package, so it's 1 package dropped. So in the node 2, we can also do the same thing, and it will show us 2. So the number in the matches increase because like it does drop the ABCDEFG pattern. So let's try a node 3, And we do the same thing. It will also increase the match values. Okay, that's all our demonstration. Thank you for watching.